Hi all, once again welcome back to Chemist. So today we'll have the part 11 of the question paper discussion that we were so far discussing, and today's video is exclusively for elimination reactions in organic chemistry, and the video contains only one question that is based on this elimination reaction, but uh, I'm just discussing all the important aspects of this reaction. For those who have not gone through the previous videos, if you're interested, you can go through. I'll be giving the link of the same in the iCard above. And without wasting much time, let's move on to the question. So the question for this video is question number 37 of the question paper. It is a question which is based on E2 reaction, which is a kind of elimination reaction. In E2 reaction, the dihedral angle of syn periplanar conformation is option A 0 degree, option B 90 degree, option C 120 degree, and option D 180 degree. I think you are familiar with the substitution reaction. So because in the previous video we had a discussion regarding the same. So this is a reaction which is in particular the SN1 reaction. You are having a tertiary halide, and that will react with a nucleophile, in particular ethanol, which can give a potential ethoxide as the nucleophile, and that will undergo substitution. Instead of chlorine, you will be getting this OET group, and this is the product that we get. Okay, so this is an SN1 reaction, and it is a substitution reaction in which an atom is substituted by another group of atom, which is OET minus. Now what happens when you are having a elimination reaction? That is the same substrate that can undergo an elimination reaction. That is, instead of substituting this chlorine with some other ligand or some other group or atom, instead a hydrogen atom from either from this side or this side is eliminated to produce the alkene. Okay, so I'll just write down how this product is being formed. That is, suppose this is the substrate that you're having. So instead of substituting this chlorine atom with the with some other group, you are actually eliminating a hydrogen atom along with chloride ion. So this is the product that you are getting. That is, this hydrogen atom is removed along with the Cl, may be eliminated as a molecule of HCl, and this forms a double bond here. So this is what is known as an elimination reaction. So if you are in particular, if you want to specify the type of elimination reaction, it is an E2 elimination. So we'll come to that designation later. We'll have the classification for elimination reaction in the coming slide. Okay, so this is what is meant by elimination reaction. So how can you get such a product? So you were having both the substrate were the same. In this case, you are having a substitution reaction, but in this case, you are having an elimination reaction. So that is actually taking place because in this case, you are not having ethanol as the reagent. Instead, you will be having ethoxide ion, that is ETO minus as the reagent. That is, instead of ethanol, if you are using ETO minus, that will have a tendency to abstract a proton from the adjacent carbon atom, which will lead to the further reaction to form an alkene. Okay, so whenever you are having a strong base, then elimination will be favored over substitution. So I have just given the mechanism for both the reaction on the right hand side. So this is how you get this particular product. That is, initially you will get a carbocation by the dissociation of the leaving group, that is chloride ion. I think you are familiar with SN1 reaction. It is a two-step reaction. The first step involves the formation of a carbocation, and in the second step a proton is being a proton is eliminated, at the same time the ethanol is getting coordinated to the carbocation to form the substituted product. Now in the case of elimination, the mechanism is different. This is how the mechanism takes place. That is given in a better way here. E2 minus will abstract the proton. At the same time, the chlorine atom will be eliminated to form the final product. So what is making the difference in the reaction? You are having the substrate as the same, but both the reactions are different. One is a substitution reaction and the other one is an elimination reaction. The difference is actually made by the reagent that we use. Ethanol and E2 minus both can act as a base. But when you are having a stronger base like ethanol, always alkoxide ion is a stronger base than alcohol. That is, if suppose you are having an alcohol, say ROH, and the corresponding alkoxide ion is RO minus. This has got higher basicity compared to this ethanol. Okay, so when you are having a strong base or alcohol, strong base, elimination is favored over substitution. So this is what is meant by elimination reaction, and I think you might have got an idea regarding the difference between elimination and substitution reaction. Now coming to the other factors which favors elimination over substitution. The second factor is actually the nature of nucleophile. Initially, we were having a factor which also depends upon the nature of nucleophile. There, we were having a comparison of nucleophile in terms of their strength. That is, when you are having a strong nucleophile, you will get elimination. When the nucleophile is weak, then strong nucleophile in the sense, when you are having a nucleophile which is more basic, you will get elimination. When you are having a weak nucleophile or nucleophile which is a weak base, then you will get substitution. But here the point is somewhat different. Here you will be comparing the steric features of nucleophile. That is, when you are having a bulky nucleophile, elimination is favored over substitution. So let's see how this is happening. For example, if you consider this particular case, you are having tertiary butanol. It is a substrate that can actually produce a stable carbocation. So definitely SN1 can be or SN1 is also possible for this substrate. But when you are using a HBr as the substrate, as the reagent, that is, you are using HBr as the reagent, which is having potential H plus and Br minus. So the first step will be the conversion of OH into a better living group. So when you are having OH and H plus, normally the protonation of OH will take place, and that will lead to the formation of OH2 plus. So I would like to mention a point here. OH minus or OH group is not a living group. It usually don't act as a living group. So when you are having OH group, you have to convert that OH group into a better living group. Most probably, you'll be protonating it to form the OH2 plus, which will be a better living group, because this can exist as a neutral molecule, H2O. Therefore, this will easily undergo elimination, or it will detach from this carbon to form a carbocation here. But in one of the elimination mechanism, which is known as the E1CB mechanism, OH will act as such as a living group. In all other cases, you cannot see OH acting as a living group. In order to remove that OH, you have to convert it into a better living group, and one of the options is to protonate it to convert it to OH2 plus. Okay. Now this is what is taking place when you protonate. Now after protonation, this is a stable molecule, so it can leave the system to form a carbocation. So this is the first step, and this is the slow step. Therefore, this will be most probably the rate determining step. Now in the second step, you are having the nucleophile Br minus, that will be adding to form the substituted product. So here, when you are using HBr is not a bulky nucleophile. HBr is actually producing a nucleophile which is Br minus, but you are also having H plus as the counter ion, which will help in the elimination of the living group to form the carbocation, which is then attacked by the nucleophile to form the substituted product. Now, if you carry out the same type of reaction with the same substrate, again you are considering the tertiary butanol. But this time, instead of HBr, you are having H2SO4. H2SO4 is also an acid, and it will be ionizing to form H plus and HSO4 minus. Okay, this is the structure of HSO4 minus. Now carry out the same reaction with the substrate. Initially, here we were having a protonation. Here also we'll be having a protonation, so that this OH2 will be leaving the system to form a carbocation. But the counter ion for H2SO4 was H2SO4 is actually HSO4 minus, which is a bulky nucleophile compared to Br minus in the case of HBr. Since Br minus is not that sterically big ligand or a bulky ligand, it can approach the reaction center to get the substituted product. But that is not the case with this HSO4 minus. It is a bulky group, so it cannot approach this reaction center because there is steric hindrance. There will be steric hindrance. So it will be approaching the nearby hydrogen atom attached to the neighboring carbon, and it will be abstracting that proton, which leads to the formation of a alkene instead of a substituted product. So this is the difference between elimination and substitution. So when you are having a less bulky ligand and less bulky nucleophile like Br minus, which is produced from a reagent HBr, you will be getting the substituted product because Br minus is not that high, not that large. So it can approach the reaction center to form the tertiary butyl bromide. But when you consider H2SO4, it leads to the formation of a bulky nucleophile, which is very difficult difficult for this nucleophile to approach the reaction center. Therefore, it will be abstracting the proton from the neighboring carbon to form an alkene. Okay, so I think it is clear. So when you are having a bulky nucleophile or a base, elimination is favored over substitution. For the time being, we will consider one more example for this one. So suppose you are having a substrate like this. Okay, so this is a bigger substrate that you are having. So it is not OH minus, it is Br. Okay, so this is the alkyl halide you are having. And in the first reaction, you are using KOH as the nucleophile or the reagent. Then what happens is that OH minus will be the nucleophile which is donated by this KOH. It will be attacking this carbon atom. This is the reaction center, and this Br minus will be eliminated, so that you will be getting the product, this one. Instead of Br, you will be having OH. So this is a kind of SN2 reaction because it is a primary carbon atom. Okay, so the reaction center, that is the carbon atom which is having this bromine, is a primary carbon atom. Now suppose you are considering the same substrate. So this is the substrate that you have, but instead of KOH, suppose you are having another bulky base which is potassium tertiary butoxide. Okay, potassium tertiary butoxide, if you consider the expanded structure, this is the structure of potassium tertiary butoxide. Okay, this portion is abbreviated as TBU. This is tertiary butyl group. Okay, so when you are having this bulky group, you cannot expect an SN2 reaction because this is a bulky nucleophile that we are having. So this bulky nucleophile cannot approach this reaction center and displace this bromine. Instead, it will be attacking the neighboring hydrogen atom of the neighboring group. That is, you have to actually write this O tertiary butoxide, anion of tertiary butoxide here. That is, this hydrogen atom will be attacked. So here this bond will be shifted to this side and bromine will be eliminated. So that you will be getting the product. This is the product that you get. So this is an alkene. So normally in all elimination reaction, you will get alkene as the product. So in this reaction, I think this example is clear. So when you are having KOH, an SN2 reaction will take place, and that leads to the formation of a substituted product, an alcohol. But when you are using a bulky base like tertiary butoxide, potassium salt of tertiary butoxide, it is not able to attack the reaction center and eliminate bromine. Instead, it will be attacking a hydrogen atom on the adjacent carbon to form an olefin. Okay, so this is about bulky nucleophile favoring elimination reaction. Now coming to the third factor which favors elimination is high temperature. So when you are having a substrate which is able to form a more stable carbocation, at the same time when the temperature is higher, then elimination will be taking place. So we can understand the kinetics of this point in a detailed manner. For example, if you consider substitution reaction, in substitution reaction, a substrate A will react with a reagent, and a product C is being formed in which an atom or a group of atom is being substituted by B. So D will be eliminated. That is, it is the leaving group. So A plus B is equal to C plus D. So when you look at the change in the entropy, that is equal to 0, because on left hand side and the right hand side you are having equal number of members. Okay, so delta is equal to 0. But when you consider elimination reaction, this the condition is different. That is, A plus B will be giving C plus D plus E. So 3 products will be actually formed. So you can consider this example in order to understand it better. So this is A, this is a substrate A, and this is B, the base that you use. And when it undergoes an elimination reaction, you will get a byproduct water, an alkene as the main product, and at the same time an anion, Br minus is also, the leaving group is also generated. So in this case, when you consider the delta S value, that is 3 minus 2, which is equal to plus 1. So for elimination reaction, delta S is having a positive value. So when you, I think you will be familiar with this equation, delta G, which is an equation for thermodynamics, delta H is equal to delta G is equal to delta H minus T delta S. So for a reaction to be favorable, delta G should be negative. Okay, higher negative value of delta G is a factor which favors a reaction. So delta S is positive. So this factor is positive. So in order to make this whole factor, that is T delta S, more positive, you should increase the value of temperature. That is why when you are having high temperature, it favors elimination reaction. But when the temperature is increased, it has nothing to do with the substitution reaction because delta S is 0. But in the case of elimination, since delta S is positive, when temperature increases, the delta G for the reaction becomes more and more negative, and elimination is favored over substitution. So on the whole, to summarize, we can say that there are basically 3 factors which favors elimination. First one is nucleophile that are strong bases. Second one is nucleophiles that are bulky. Third one is high temperature. So when you have these conditions and a substrate which can undergo both substitution and elimination, elimination will be favored over substitution when the conditions are like the one which is shown in the slide. So that is about, that is how you distinguish between elimination and substitution reaction. And also, if you are provided with a substrate, you can arrive at a conclusion that the substrate will undergo this elimination or substitution based on these factors. Now we'll have the different classification for elimination reaction. As shown in the slide, there are basically 3 different types of elimination reaction. There are some other reactions like pyrolytic elimination, which is known as the EA mechanism and all. But that comes under pericyclic reaction. So when you consider normal organic reaction, these three are the different types of elimination reaction that we have. The first one is E1 elimination. Now, E stands for elimination. 1, 2, etc. That stands for the kinetics. That gives an idea regarding the kinetics of the reaction. For example, if you consider SN1 and SN2 reaction, SN1 is because the rate depends only on the concentration of substrate. In the case of SN2, rate depends on both the concentration of substrate as well as nucleophile, because the slow step involves both the components. The same is the case with elimination reaction. When you consider E1 reaction, it means that the rate of the reaction just depends upon the concentration of only the substrate. So this is the mechanism of E1 reaction. So this is the substrate that we have. This is the proton that is normally eliminated, and this is the living group. In the case of E1 mechanism, that is a two-step mechanism in which in the first step, a living group will leave forming a carbocation. That is the slow step. Therefore, the rate only depends upon the concentration of the substrate. In the second step, a proton is being eliminated, and that is abstracted by the base that we use in the reaction to form the final product, which is the olefin. Okay, so living group will leave first, and then, sorry, this is and then deprotonation will take place. Now coming to E2 reaction, E2 is somewhat related to SN2. That is a single step reaction in which both the abstraction of proton, that is deprotonation, and the loss of the living group will be simultaneous. That is both of them occurs at the same time. Therefore, the rate of the reaction will depend upon the concentration of the substrate plus the base that we use. Okay. So this will again lead to the formation of olefins. So both the loss of living group and elimination occurs simultaneously. E1 CB is very much different from both E1 and E2. In this case, this is possible only when you have a particular type of substrate. That is substrate which have an anion stabilizing group. That is a group which can stabilize a negative ion. When you are having such a kind of group, even CB is possible. In that case, so suppose this is the anion stabilizing group. Most probably double bond carbonyl group, cyanide group, nitro group. These are anion stabilizing group. So when you have such type of group, in the first step, the proton will be eliminated. That is, deprotonation will take place, resulting in the formation of an anion. And that anion is stabilized by this anion stabilizing group. That is, this anion, the bond can be shifted to this anion. And in the second step, when it combats, it will eliminate the living group, and that is the slow step. That is, even in the case of E1 CB, the steps are just opposite to that of E1. In the E1, first the living group will leave, or the loss of the living group will take place. But in the case of E1 CB, the loss of proton, that is deprotonation, will take place. In E1, second step is deprotonation. In E1 CB, second step is the loss of the living group. And okay, so here I have made some mistake. Here it is not both the loss of living group and elimination occurring simultaneously. Instead, you will be having the deprotonation first. Deprotonation first, followed by elimination of living group. Okay. So this is how you distinguish between three different types of elimination reaction. Now we'll see the important points regarding each elimination in detail. So we'll begin with the E1 mechanism, which is elimination unimolecular. So as I've already mentioned, here the living group will first leave in a slow step, which is the rate determining step to form the carbocation. And in the next step, the base will abstract a proton from the carbon adjacent to the carbocation center to form the alkene. Therefore, in the first step is the slow step. So it involves only the substrate. Therefore, the rate depends only on the concentration of substrate. Now, E1 describes an elimination which is in which the rate determining step is unimolecular and does not involve base. The leaving group leaves in the step and the proton is removed in a separate second step. So, it is a two-step mechanism. So, this is what is meant by E1 mechanism. And E1 can occur only when the substrate can ionize to give a relatively stable carbocation. So E1 is somewhat similar to SN1. In SN1 also you need a stable carbocation. So here also you should have a stable carbocation for E1. So these are some of the cases where you can have a stable carbocation and the final product that you can get. And another point regarding E1 reaction is that it is regioselective. That is, regioselective means the position of double bond have certain orientation. That is, in this particular case, you can actually have two different olefins. That is, I'll show how this two olefins are being formed. So this is the substrate that you have. And you can see that the reagent is HBr. So in the first case, the proton will be added that will convert the OH2, OH into OH2 plus, which is a better leaving group. So this will leave to form corresponding carbocation. So the formation of carbocation is very important in E1 reaction. Now after the carbocation is being formed, the base. So in this particular case, Br minus will be acting as the base. That base can abstract a proton from two different sides. That is, either this proton can be abstracted. So this will lead to the formation of this particular product. In other case, it can also abstract a proton from this hydrogen. So this carbon. That is, this proton can also be abstracted. There are two different possibilities. So in this particular case, you will be getting a product like this. Okay. So this is B and this is A. So this is A and this is B. But when you consider E1 reaction, you can see that product A, that is this one, will be the more substituted product, the major product. And the major product is the one which is more substituted. So even elimination, it always leads to the formation of more substituted alkene. That is the regioselectivity of even reaction. So when you need not have any confusion regarding the product of an even reaction. So whenever you are having an even reaction, both the product will be formed. Okay. It is not regio-specific. When it is specific, you will get only one type of product. Selective represents both the product will be formed. One will be the major product and the other one will be the minor. Okay, so when in this particular case, there can be the formation of the more substituted as well as less substituted olefin, in which the more substituted olefin will be the major product. So this is the point regarding the structural importance of the substrate and as well as the regioselectivity of the reaction. Now coming to E2 mechanism, which is elimination bimolecular. So this is somewhat related to SN2 reaction, in which both the addition of nuclear, in SN2 we have the addition of nucleophile and loss of leaving group as a simultaneous step. Here also the deprotonation as well as the elimination of the leaving group is simultaneous. Therefore, both of them are involved in the rate determining step. Therefore, the rate depends upon the concentration of both the base as well as the alkyl halide. Okay, so this is what is written here. Now, the importance of E2 elimination is that E2 elimination is actually based on some stereoelectronic requirement. That is, the substrate should have a particular type of arrangement of the hydrogen that is eliminated as well as the leaving group in order to undergo elimination reaction. So in the E1 case, there is no importance in the structural arrangement of the hydrogen atom and the leaving group. It can be, there is only one condition, that it should form a more stable carbocation. But that is not the case with E2 elimination. In the case of E2 elimination, the eliminating group and the hydrogen that is deprotonated, both of them should be in opposite side. That is, they should have a anti-periplanar transition state, that is anti-periplanar conformation. That is what is meant by the stereoelectronic requirement for an E2 elimination. That you can understand from these two figures. This is the syn periplanar conformation. In syn periplanar, you can see that both the leaving group and the hydrogen atom that is being eliminated are on the same side. And this is the Newman projection for this particular arrangement, that is syn periplanar. So it is an eclipsed arrangement. So actually we are having the question from this part. So they have asked the dihedral angle, that is angle between this hydrogen and X that is eliminated in the syn periplanar conformation. Here you can see from the figure, it is well clear that the dihedral angle when you are having syn periplanar conformation is actually 0 degree. Okay, 0 degree. Whereas in the case of anti-periplanar, actually this should be the condition for E2 elimination. For E2 elimination to take place, the leaving group as well as the deprotonating hydrogen atom both should be opposite. That is, they should be anti-periplanar. That is staggered arrangement. So in this arrangement, you will be having the dihedral angle as 180 degree. Maybe this will be asked in some other question, some other exams. So you can just note it down. So this is what is meant by the stereoelectronic requirement. So when you are having this condition, actually the product will be formed, but that will be the minor product. But when you are having anti-periplanar conformation, that will lead to the formation of major product, and that can be understood from this example. So this is a secondary alkyl halide, and NaOET, that is ETO minus is the base that you are using. Then there is possibility for two different alkane to be formed, but one will be the major product. This is the major product and this is the minor product. You can see that this minor product is actually formed from this conformation, and major product is formed from this conformation. And in both the cases, you can see that the hydrogen and the bromine atoms are anti-periplanar. So this both of them actually satisfies the condition for an anti-periplanar transition state. That is why you are getting both the product. But this is favored. This is major product because this is a trans alkene, and the bulky groups are on the opposite side. But this is a cis alkene which is less stable compared to trans alkene. Okay, that is why one is major and the other one is minor. But both of them satisfy the condition for satisfy the stereoelectronic requirement. Plus 19% of this olefin is also formed, and this is the one which is from the syn periplanar conformation. That is why it is very formed in very small amount. Okay, so that is about the stereochemistry of elimination. Now we'll just have an idea regarding the two rules in elimination reaction, which is Zaitsev rule and Hofmann rule. Zaitsev rule, I think you might have heard about it from lower classes or all. That is, Zaitsev rule states that elimination will lead to more highly substituted olefin. That is, in this case, you can see that there are two olefin that is being formed. This is the more substituted one, and that is formed as the major product. But another rule is also there, which is known as the Hofmann's rule. And in Hofmann's rule, less highly substituted alkene will be formed as the major product. So here you can see, in this case, this is a less substituted olefin, but that is formed as a major product. And this is also a less substituted olefin, which is formed as a major product. But you can see that there is a condition for this Hofmann elimination. In Hofmann elimination, the leaving group is actually a bulky group. And the use of sterically hindered base raises the activation energy barrier for pathway to product predicted by Zaitsev rule. And it is actually, one thing is the leaving group. Leaving group will be bulky. In most probably, when you are having a tertiary ammonium group as the leaving group, you will get the Hofmann elimination. That is less substituted product. And when you are having a sterically hindered base also, this Hofmann rule is more pronounced. Okay, so that is about Zaitsev rule and Hofmann rule. So one actually it leads to uh, Zaitsev rule leads to the formation of thermodynamically more stable product, but Hofmann rule leads to the kinetically more stable product. Now coming to the third mechanism, which is known as the even CB mechanism. This is known as elimination unimolecular via conjugate base. So we have already gone through the even CB mechanism, the general representation for even CB mechanism. That is, as I've already mentioned, even CB is possible only when you are having an anion stabilizing group like carbonyl group, nitro group, cyano group, etc. Because in this case, initially the deprotonation will take place and the anion that is being formed can be stabilized by resonance to the anion stabilizing group like this. So this can be delocalized towards oxygen. Now it delocalizes in the backward direction. This X is being eliminated. That is, leaving group is lost in the second step. It is just reverse of even mechanism. In even, leaving group leave first and deprotonation second step. In even CB, deprotonation is the first step and leaving group loss of leaving group is the second step. So in this case, in the case of even CB, this also takes place in two steps. First step is the formation of anion. Second step is the elimination of leaving group. But the second step is the slow step and that is the rate determining step. Therefore, the rate depends only on the concentration of this conjugate base, that is the anion that is being formed. The anion is usually represented, designated as the conjugate base. So, the rate of the reaction depends only on the concentration of conjugate base. That is why the name is like even CB. Okay. This is another example for even CB mechanism. So whenever you are having a substrate in which you find that some group, some anion stabilizing group is there, then you can actually trace out the mechanism as conjugate base. That is, you can trace for this conjugate base mechanism. For that, initially you have to identify what is the anion stabilizing group, what is the leaving group, and what is the which hydrogen atom is being eliminated. For example, I can show this in this particular example. So here you can see that there is an anion stabilizing group. Okay, CO2ET is actually C double bond O OET. Okay, so this is the anion stabilizing group that you have, that is A. And you are also having a leaving group. As I have already mentioned, OH is not a better leaving group, but only in even CB, OH will act as a leaving group as such. You need not protonate. That is the importance of even CB. And in between these two groups, that is anion stabilizing group and the leaving group, you should have the proton that need to be eliminated. Then only you can write out the mechanism. So if you are having a group like this, initially you have to identify the anion stabilizing group, which is the anion stabilizing group, then the leaving group and the hydrogen atom that need to be protonated. So initially the hydrogen atom will be protonated so that that bond can be shifted to the C double bond O of the anion stabilizing group, and when it comes back, when it delocalizes in the backward direction, this OH group will be removed. But since in this particular case you are having mesetyl chloride is a bulky group. So the function of mesetyl chloride is to convert this OH into some better living group, OMS, say OMS. So in this case, OMS will be acting as the leaving group. If MsCl, that is mesetyl chloride, is not present, OH as such can also act as the leaving group. But since in this reaction we are having MS chloride, you can actually convert this OH into OMS. Otherwise, it is not possible. It is not required. You can actually eliminate OH as such. Okay, so then you'll get the final product. So if you consider the stereochemistry of the product in even CB, you cannot say that it is a highly substituted olefin or a it doesn't require an anti-periplanar conformation and all. Here the position of double bond always will be fixed. That is, you are having anion stabilizing group here, leaving group here. So in this case you can have the double bond only in this position. You cannot have any other position because the mechanism is like that. You can actually remove only this proton to get this particular mechanism. Therefore, the position of double bond, you need not have any confusion regarding the position of double bond in E1CB because that will be fixed in one position, cannot be altered. Okay, so that's all about E1CB. So finally, to summarize, so this is a very useful table. So you can just note it down. So when you are having different types of substrate, in which conditions you can get different types of substitution and elimination reaction. Methyl chloride, you can see that when the nucleophile is poor, you don't have any substitution or elimination reaction. Whereas if you are having if the substrate is a methyl chloride or a methyl group, even if you are using a weak base or a strong base or a strong any type of base, hindered base, you'll be getting only SN2 mechanism. No E1 or E2 or even CB or SN1 is possible. Instead, if you are having primary alkyl halide, which is an unhindered one, then when you are having weak or strong basic nucleophile, substitution will be taking place. And when you are having strongly basic nucleophile, which is also hindered, then you can get an E2 elimination. So in similar way, you can have different combinations of reaction, substitution and elimination reaction. So this is a very important table that you can note it down. Now coming back to the question, we have already discussed it in a discussion regarding E2 reaction, but finally to conclude, we'll see it again. In E2 reaction, what is the dihedral angle? As I've already mentioned, in E2 reaction, it has a stereoelectronic requirement that the leaving group and the hydrogen that need to be deprotonated should be in anti-periplanar conformation. But in anti-periplanar, you'll be having a bond angle of 180 degree, and in the syn periplanar you'll be having a bond angle of 0 degree. Therefore, the right answer for this question is option A. So that's all for this question. So with that, we have come to the end of discussion regarding elimination reaction, and in the coming video we'll be having the other following questions of the question paper. So I'll be coming soon with that. So till then, see you, take care and bye bye.